Hi everyone. In this video, we are going to talk about calculus of matrices. We already know what are matrices and how to work with them, how to use them to solve linear systems. Right now, we are going to talk about using specifically calculus operations like differentiation and integration toward matrices. Well, basically for this class, we will need actually only differentiation, but let's kind of talk about both. So, how are we going to use calculus on matrices? Well, imagine that we have a matrix A with coefficients A11, A12, A21, sorry, 21, 21, and A22, 2 by 2 matrix, right? Imagine that every function of this matrix is actually a function which depends on variable t. So it's not like just a coefficient, but that's a function depends on variable t. Then the whole matrix A is going to depend on variable t. And that's not matrix anymore, but it's going to be a matrix function. Matrix function. For example, A of t. Again, I'm using 2 by 2 matrices, but you always can extend it to something bigger. I'm going to create a matrix which consists out of 4 different functions. T squared for A11, sine of t for A12, and e to the power of t for A21, and ln of t for A22. Well, just to kind of represent any variable function. We also can have vector functions. Remember that we can have vectors. Vectors are kind of short matrices, right? A vector function x of t is going to be some vector. For example, for 2 by 2, it's going to consist out of 2 entries, x1 and x2, and they're going to depend on t, and they can be known or unknown. That's a vector function. Okay, what are how we apply calculus to this vector matrices? Well, for example, if your all coefficients of the matrix, vector coefficients of the function coefficients of the matrix are continuous at certain point t0, if all aij of t are continuous at t equals t0, then the matrix which is made out of these coefficients is going to be continuous at t equals t0. Well, if all of them are differentiable, the matrix is differentiable. I'm going to just maybe write differentiable. Everything here is same. Differentiable. Then let's say everything same is going to be differentiable. How it's going to look? Let's just differentiate something like what we have already defined over here, right? What is going to be, for example, derivative of the matrix A of t, which we defined in the beginning. So what is dA over dt? Well, to differentiate it, we just need to differentiate every coefficient. So in our case, it's going to be 2t, and the derivative of sine is cosine of t, and derivative of e to the power of t is e to the power of t, and derivative of ln is 1 over t. So that's how we differentiate the matrix. Well, we also can integrate the matrix, of course, if you can integrate each function. So let's integrate. Let's calculate integral of this matrix of our derivative. It's not going to be too complicated because we already kind of know what we differentiated, right? If I put under the integral matrix 2t cosine of t e to the power of t and 1 over t. And let's say integrate it. Can be indefinite integral, or it can be definite integral. If you have indefinite integral, you are going to have a constant matrix to add. Let's do both. So I'm going to integrate each function here, and this is indefinite integral, does not have limits, right? So I integrate each function separately here, and I'm going to get t squared, and the cosine is going to give me sine of t, and exponential function e to the power of t, and 1 over t is going to give me a ln of t, and there is going to be a matrix of constants. Well, I'm just going to label them C1, C2, C3, C4, because each of these four functions is going to get its own constant, and I'm just separating constants separately from variables. So this is indefinite integral. If you want to do a definite integral, we can do something like this. Take the very same integral, but put some numbers here. For example, I don't know, let's calculate it from 1 to 2. Well, again, well, we already know the result of integration, right? So 2t cosine of t. I'm just going to do the very same integral, but use my limits. dt is going to produce for me matrix t squared sine of t e to the power of t ln of t, and the limits are from 1 to 2. So I'm just going to plug in 1 and 2 into every function. For example, for t squared, 2 squared is 4 and 1 squared is 1, so it's 4 minus 1. For sine, well, it's going to be sine of 2 minus sine of 1. Numbers are not very good for sine, right? For exponential function, e squared minus e to the power of 1. And for logarithmic, it's going to be ln of 2 minus ln of 1, which is 0. All right, and we are going to have something like this. Yeah, we can calculate 4 minus 1 is going to be 3, but otherwise it's going to be like this. Okay, so what other things we need to know about matrices? Well, we can apply differentiation rules to matrices as we do it for functions. Let me kind of scroll this a little bit up, and I'm going to write down differentiation rules. Well, what are differentiation rules? Remember, we had a rule that if you multiply a function by a constant, when you differentiate it, you just differentiate function, but constant goes in front. Well, for matrices, everything same is going to be true. Just instead of constant numbers, we are going to have constant matrices. Imagine that you have constant matrix C multiplied by variable matrix A. How do we differentiate it? We can take constant matrix C outside and just differentiate matrix A, which is variable matrix. I'm going to write down in parentheses that C is a constant matrix. Sorry. What else? Well, a sum of two matrices is going to produce a sum of derivatives of these two matrices. So if you have matrix A and matrix B, to differentiate the sum of them, you differentiate each one separately. All these rules are coming from essentially the definition of differentiation of the matrix. So you differentiate every term in here, right? Well, when you add these two matrices, then you differentiate every term. Every term is just a normal function. It follows normal function rules, and that's going to just create a sum of two functions, which you can always separate into here. Right, I'm not going to prove them because they are very, very kind of simple. Well, for product rule, a little complication for product rule. Remember that the product rule is going to produce a product of derivative and the function, right? That's a product of two function matrices. So you differentiate the first matrix and multiply by the second, plus you copy the first matrix and differentiate the second. For normal numbers, it was not very essential what to put first, matrix, the differentiated function or not differentiated. For matrices, we will need to keep the order, because remember, when we switch matrices, the result of multiplication is changing. So if your matrix A comes first, it's going to stay first in a derivative and as a factor. Matrix B comes second, stays second as a factor and as a derivative. Okay, so I'm going to write down in parentheses to keep same order, order of A and B in products. Okay, what else do I need to do? Well, I'm going to consider several examples of all these rules and explain how are we planning to use all this stuff. Again, not everything what we had in this review we are going to use in my lectures. Basically, we're going to use very few things actually. We are just going to use a multiplication and solving equations. But unfortunately, if I just explain these two things, you're not going to understand them because they come like a whole package of matrices and all these linear systems. I'm going to do differentiation as a first example. Let's do example 1. I'm going to differentiate a product of a constant matrix 1, 2, 3, 4 by a vector matrix, which is going to be just a vector of sine and cosine, two functions. I'm going to differentiate this. So I'm going to take the matrix 1, 2, 3, 4 outside and just differentiate sine and cosine. Cosine is going to give me minus sine. Sine is going to give me cosine. So that's going to be my derivative. And if you wish to know what is going to be the result, you can multiply actually these two matrices and get something. I'm going to do multiplication. So 1 by sine is going to give me minus sine of t plus 2 cosine of t. And I multiply 3, 4 by sine and cosine minus 3 sine of t plus 4 cosine of t. That's going to be my final result. My final result is vector, right? Because I finally multiply. Well, I'm not gonna do the differentiation of a product because I don't think that we are going to have differentiation of two variable matrices, but well, it works same way. I'm going to talk a little bit about how are we planning to use all this matrix stuff in differential equations. We are going to use it to solve differential equation systems. Systems means that you combine several differential equations together. And of course, each differential equation is about its own function, and you try to solve them together. Let me write down differentiation equation system. Example number 2. So imagine that we have a system of differential equations and variables here are x's and independent variable here is t. So we have two dependent variables, x1 and x2. x1 of t plus x2 of t. And that's my first differentiation equation. So x1 prime equals x1 plus x2. And x2 prime, usually we separate derivatives from the functions, is minus 2x1 of t plus 4x2 of t. That's a system of two equations, and we solve them together because they are kind of mixed with each other, right? That's the equation about x1 is not only about x1, but also including x2, and x2 is including x1 too. So step number 1, we are going to write down this system of differential equations into a matrix form. First, we are going to define a vector matrix of variables. They are going to be x1 of t and x2 of t. They're my dependent variables. Functions which we are searching for, they are unknowns. Second, what is this? This is actually the product of matrix A by the vector of my unknowns. How matrix A is going to look? Matrix A is going to look like 1. You just copy the coefficients 1, 1, and minus 2 and 4. And we already defined what is x. It's x1 and x2. Well, you can just check, multiply this 1, 1 by x1, x2. You are going to get what? 1 by x1 plus 1 by x2. Remember multiplication rules which we had in the review, right? Minus 2x1 plus 4x2. I just multiplied these two matrices, vector and matrix, and I got my right side of equation, right? x1, x2 minus x1 plus x4, x2. And here on this side, we are going to have a derivative of vector x. So if I write it down in a matrix form, I'm going to get something like this. X prime of t equals, I'm going to copy the matrix. Usually you can just write down letter, but I'm going to copy the matrix to show specifically that we are using this matrix. And then vector x again of t. So this is differential equation in a matrix form. And basically, guys, we are going to learn how to solve them. But because this is a review of linear algebra, not like we are not doing solutions yet, we are going to just check if something is a solution of this differential equation system. So the question is x of t, which equals, I'm sorry that sometimes I have to kind of do, sometimes my computer thinks that it knows better than I do know. Vector consists out of e to the power of 3t and 2e to the power of 3t. We are going to check if this vector is a solution of this system. A solution. Solution means that it turns it into a true statement, that the left side is equal to the right side. Well, I'm going to start with the left side. Left side is x prime, right? So I'm going to differentiate my vector. X prime is going to be what? Well, differentiation of exponential function is exponential function itself, and 3t is going to give me 3 in front of the function. Here, the same story, we are going to have 2 by 3e to the power of 3t. By the way, guys, when you have the same factor here, you can take it outside. It's not necessary to do, but I'm going to do it just to show you the opportunity to write it down like this. So you can keep numbers inside and take the same factor outside of the matrix. And it does not matter how big is the matrix. If all entries of your matrix have the same factor, for example, 2, you can take it outside of like the matrix. Well, I think we talked about this in the review, but just remind you. Now we are going to check the right side. Right side is just this vector multiplied by a matrix, right? So my right side is 1, 1 minus 2, 4 multiplied by e to the power of 3t and 2e to the power of 3t. Is it going to give us the same expression? Well, I'm going to multiply 1, 1 by this vector. So I'm multiplying 1 by e to the power of 3t. It's e to the power of 3t. And another one is 2e to the power of 3t. So I multiplied this one by this. Now I'm going to repeat it for the second row, and it's a minus 2e to the power of 3t. Multiply this 2, right? And multiplying this 2 is going to give me 2 by 4 is going to give me actually what? Plus 8e to the power of 3t. And that's my result. Right now, I'm going to modify it a little bit by adding the numbers. I have 3e to the power of 3t. And here I have 8 minus 2, which is going to produce 6e to the power of 3t, right? And here I can actually just compare these two numbers, or I can take e to the power of 3t outside, and I have 3 and 6 e to the power of 3t. You see that my left side and my right side are kind of same, right? Because we have a same expression. You can compare this expression, or you compare this simplified form. So it is a solution because our equation is becoming a true statement. Conclusion, it is a solution. Okay. Well, now maybe I think that's all. We did the integral already, right? We kind of brushed everything up. Again, you can always read this sections 2 and 3, 9.2 and 9.3 from your book. But I suggest you to watch also my review videos, because I try to simplify the material as much as possible, because if you did not take linear algebra yet, it's going to be really hard to learn it in like 1 week, because that's a lot. Okay, that's all. Thank you very much. And I'm going to post it, of course, online.